Welcome to this next video in the playlist on ring theory. In this video, what we're going to introduce is the concept of an integral domain, often just called a domain, which is a special type of ring algebraic structure. Okay, now the first thing to say is that this has absolutely nothing to do with integration. Okay, so don't see the integral domain here and think that this has anything to do with integration. It doesn't. Okay, it's just some name that someone once came up with. Okay, so let's begin then. Let's see what the definition of an integral domain is, then let's have a look at some examples, and then let's see the important cancellation law that's going to be true in integral domains. Okay, so firstly then, what is the definition of an integral domain? So an integral domain is just a special type of ring. Okay, now we usually denote it capital D. Okay, so it's going to be a set of symbols with an addition composition law and a multiplication composition law defined on it. Okay, now what sort of a special type of ring does it have to be? Well, it has to be a non-zero commutative ring which obeys the property that if you have two elements multiplying together to give the additive identity in the ring, it implies that one of them has to be, well, at least one of them has to be the additive identity. So let me write this out. So the first thing to say is that an integral domain is a commutative ring. Okay, so that's the first condition that I should put here. Okay, the introductory one. So it's a special type of commutative ring. So it's a set of symbols with an addition and multiplication law defined on it that obeys all of the axioms of a commutative ring. Okay. The second thing I should add is that it's non-zero. Okay, so in one sentence we can say that it's a non-zero commutative ring. Okay, so it's non-zero. Now what does that mean? I mean that it is not the zero ring. So remember, the zero ring is this stupid ring that just contains a single element, which is both the additive identity and the multiplicative identity, and the addition rule is really trivial. It's just that this element plus itself gives itself back again. The same for multiplication. It multiplies with itself to give itself back again. Okay, that's called the zero ring, and it does trivially obey the axioms of a commutative ring. Okay, however, we do not consider the zero ring an integral domain, so you need a commutative ring that is not the zero ring. Okay, so you do not consider the zero ring an integral domain. So find some commutative ring that is not the zero ring, and then we can proceed further and ask, is it going to be called an integral domain? Okay, so we have a final condition, which is the really important one, okay, the special one, the new one, because we understand all of this already. So now here comes the new condition. Okay, so if it is the case that you have two elements in the ring being multiplied together, so A and B are elements of the domain, so I'll put this here, so A and B are elements of the domain, and let's say they multiply together to give the additive identity. Okay, so you've multiplied two elements of the ring, A and B together here, or the domain, let's start calling it the domain. You've multiplied two elements of the domain together to get the additive identity. Basically, the only way this can happen is if one or both of these elements that you've multiplied together is equal to the additive identity itself. So either A is equal to 0 or B is equal to 0. So the instant you have two elements multiplying together to give the additive identity, you can instantly conclude, if you're working in an integral domain, that either A is equal to 0 or B is equal to 0, or the other possibility is that both of them are equal to 0. Okay, so to state this another way, the only way you can take two elements of the ring and have them multiply together to give 0 in that ring is if one or both of them are 0. So you can't take two non-zero elements, multiply them together and get 0 in a domain, whereas you can in a more general ring. Okay, so an integral domain is a special type of commutative ring that is not the zero ring, such that the only way that you can multiply two elements together to get the additive identity in the ring is if one or both of those elements are equal to the additive identity already. Okay, right, so that then is the conditions that an integral domain obeys. It's a non-zero commutative ring such that this is true. Okay, right. What I now want to do then is give some examples of integral domains, and the key example of an integral domain is the ring of integers. And as far as I know, the reason that integral domains are called integral domains isn't actually because the integers is an example. Okay, so it comes from something else. I think originally they were called domains of integrity. Okay, so obeying this property was considered a property of integrity or whatever. Okay, hence where integral domain came from. Okay, so the integers, however, is a key example of an integral domain. Okay, so let's just think about the ring of integers. So the ring of integers is the set of all whole numbers with the normal addition and multiplication laws defined on that set of symbols that we learned in primary school. Okay, so this is a commutative ring, and it's certainly not the zero ring. Okay, now the question is it actually an integral domain? Does it obey this final property? Okay, so is it the case that whenever you multiply two non-zero elements of the integers together, you get a non-zero element? So let's say we take, for instance, 2 and multiply it by 3. We're going to get 6. Okay, and 6 certainly is not equal to 0. So here's an example, and that sort of gives us a bit of intuition. Basically, if I take a non-zero element A and I multiply it by another non-zero element, so these are not 0, how am I ever going to have it the case that I will end up with 0 here? Okay, can you think of any whole numbers that you can multiply together, any integers that you can multiply together that are not 0, where when you multiply them together you'll get 0? Well, the answer is no. Okay, the only way to multiply two integers together and get 0 is if one or both of them is equal to 0. If you make A 0 or B 0, of course this will be true. If you make both of them 0, of course it will be true as well. Okay, but that's the only way. If you take two non-zero integers and multiply them together, you'll never ever get 0. Okay, so the integers is in fact an integral domain, and it's a key example of an integral domain. Okay, so once you've given an example, obviously the next thing to do is give a counterexample. Give an example of a commutative non-zero ring that doesn't obey the third property, okay, where you can take two non-zero elements, multiply them together and get 0. Okay, so a nice simple example of this is a modular arithmetic number system. Okay, so very closely related to the integers. So z quotiented out by 4z, a modular arithmetic number system. Okay, now we have studied these number systems. In this case, it will consist of the cosets, which will be 0 bar, 1 bar, 2 bar, and 3 bar. Okay, so here are elements of z mod 4z. These are the cosets containing 0, 1, 2, and 3 respectively. Okay, now if we consider what 2 bar times 2 bar in this z mod 4z ring here is, and I should stress this is still a commutative ring, it's a non-zero ring. Okay, all the modular arithmetics are commutative because of the commutativity of the multiplication on the integers from which they're derived. Okay, if we consider, however, what 2 times 2 is equal to, the way that we'll do this in z mod 4z is we'll take a representative from this coset, a representative from this coset. We might as well take 2 both times. We'll multiply them together in the initial integers, and of course we'll get 4 there, and then we'll take the coset that contains that answer. Okay, and which coset contains 4? Well, of course 4 is going to be in the same coset as 0, because that's the ideal that we've quotiented out by. Okay, it's all integer multiples of 4, and 4 is certainly an integer multiple of 4. So this is actually the same as 0 bar, which of course is the additive identity in this quotient ring that we've built here. Okay, so here we have two non-additive identity elements multiplying together in this commutative ring here to give the additive identity. Okay, so this is not an integral domain, basically. This is an example where you can have two non-zero elements multiplying together to give 0. Okay, right, so just to now draw a picture of what this actually means then in terms of the multiplication table. So if I draw out the multiplication table then for my integral domain here, so let's say this is my multiplication table, then the only entries in this multiplication table that are actually going to be 0 are the ones which are in the row and column corresponding to 0. So if we have our multiplication table here, of course we'll have a row dedicated to the additive identity and a column dedicated to the additive identity. And we know in any ring that the row and column dedicated to the additive identity are just going to be full of zeros as their answers. Okay, 0 multiplied by anything has to give 0 as soon as we insist on distributivity being true in a ring, which we always do insist on. Okay, so all of the answers here will be 0. So we know that the row and column corresponding to the additive identity will be full of zeros. However, in an integral domain, that's the only entries. These are going to be the only entries that are going to be equal to 0. Whenever you take a non-zero element, which is all of this portion here, all of these rows, and multiply it by another non-zero element, which is all of these portions, and this will overall correspond to all of these entries here, and I'll just colour those in. So all of these entries here, this box, okay, these are all going to be non-zero, so those are going to be the only places in the multiplication composition table that you're going to actually have zeros appearing in the multiplication table of an integral domain. Okay, so all of these entries over here are not going to be zeros, they're going to be other elements of the integral domain. Whereas that's not going to necessarily be true in a more general ring such as this one here. Okay, right, so why are these so special? Well, the big thing that integral domains have which is special is that they have a cancellation law. Okay, so I'm now going to talk about this special cancellation law. Okay, so the cancellation law is this. I'm going to state it and then we'll discuss the intuition for it. Okay, so the cancellation law is that if you have three elements of the domain, okay, so let's say A, B and C are elements of your domain capital D. And let's say it is the case that A multiplied by B is equal to A multiplied by C. Now if you're working in a normal ring, you cannot conclude from this, although you might think it would be intuitive to conclude from this. You might think it's intuitive to conclude that B is equal to C. Okay, you cannot conclude that in a normal ring. Oh, and I should add one more thing. A is not equal to 0. We assume that A is not equal to 0 here. Okay, so A is not equal to 0, and A multiplies by B to give the same answer as A multiplied by C. Obviously, if A was equal to 0, then that would be true, but we're going to assume that A is not equal to 0 here. It's more special than that. Okay, if A was equal to 0, it would be trivial that these two things were equal. It wouldn't matter what B and C were. You could set them to whatever you like, because 0 multiplied by anything just gives 0. Okay, but we're going to say A is not equal to 0, so less trivial here. Okay, and A times B is equal to A times C. You might think that it's intuitive to then conclude that B is equal to C. Now you could certainly do that in a field, because in a field, if A was not equal to 0, A would have a multiplicative inverse, and you could therefore multiply on both sides by the multiplicative inverse of A. It would cancel the A here, and you'd end up with B is equal to C. But in a general ring, we don't necessarily have multiplicative inverse for A. Okay, so it doesn't imply this. However, in an integral domain, which is a softer condition than being a field, you can conclude this anyway. Okay, now let me just give you a little bit more intuition as to what this actually means. Okay, so if we have our multiplication table here, let's say this is the row corresponding to A here. Okay, let's say that this is the column corresponding to B here, and that this is the column corresponding to C here. Okay, so once again I'll just colour my multiplication table in green here. Okay, so what I am saying here is that A is not equal to 0, so this element is not equal to 0, so that condition tells us about A here. And we are now saying that A multiplied by B, which is this entry here in the multiplication table, is equal to A multiplied by C, which is this entry over here in the multiplication table. Now the way I've drawn it here, B and C are distinct elements. What I want to prove is that if we're working in an integral domain, B and C cannot be distinct elements. Okay, but what I'm trying to show you through this picture is that it's not trivial that this is true in an arbitrary ring, because quite easily you could have these entries in this composition table as being the same element in a more general ring, but it's not going to be the case that you can have that in an integral domain, and let me explain why. Okay, so the reason that you can instantly conclude that B is actually equal to C if this is the case, i.e. you can't have it like this, B and C are the same element if their entry here is the same. Okay, so you would never have two distinct elements giving the same entry in this row corresponding to A here. Okay, so the reason you can conclude this if we're working in an integral domain is that what you can do is you can add on to both sides the additive inverse of A times C. So A times C is just some element of the ring, so you can add on its additive inverse, and you'll get now that AB plus negative AC is equal to 0. Now the additive inverse of A times C is the same as A times the additive inverse of C. Okay, you can check that very easily by asking what would happen if I added this thing onto A times C, and you can use distributivity to say that that would be equal to 0, and therefore it is the additive inverse of A times C. Okay, so I'll replace negative A times C with A times negative C here, and then I can factor out A using left distributivity, so I'll get that this is A times B plus the additive inverse of C here, and I know that that is equal to 0. But now I have two things multiplying together to give 0, and we know that we are working in an integral domain here. Okay, so if you have two things multiplying to give 0, it implies that one or the other is equal to 0, or both are equal to 0. You can't have two non-zero elements multiplying together to give 0. Now, I know that A is not equal to 0, that was the initial assumption, so that must imply, therefore, that B plus the additive inverse of C is equal to 0, and therefore add on C to both sides and you'll get that B is equal to C. Okay, so B must equal C if A times B is equal to A times C. Now, what does that mean in terms of our picture here? It means that this picture is utter rubbish. Okay, if we're talking about an integral domain, you cannot have two distinct elements up here multiplying by A to give the same answer here. Okay, so in the row corresponding to A, which is a non-zero element in the ring, you cannot have two answers appearing twice. You cannot have the same entry appearing twice in this row corresponding to A, basically. Okay, so what it means for the multiplication table here is that all the rows corresponding to non-zero elements, and indeed you can also apply this for columns as well. It could have been the other way around. You could have had A on the right here and then got the same result for columns this time. Okay, so it would also hold up that if you've got B times A is equal to C times A, that this implies that B is equal to C. So the other way around, and again we'll need the condition that A is not equal to 0 here. Okay, so if you've got the other thing like this, it will also work, so it doesn't matter which way around it is, and in this case it'll do the equivalent thing for columns. Okay, so what this overall means then is that if I look at the row corresponding to a non-zero element, okay, so let's say A here is a non-zero element, if I look at this row, no element of the integral domain can appear more than once. Okay, any element of the integral domain can only appear once. Okay, now it doesn't necessarily have to appear in the row. Of course, if we're dealing with a finite integral domain, then that will be the case, because if you've got a finite integral domain, then you've got a certain number of slots that you have to fill in this row. You're only allowed to use one element of the domain at once, so of course you're going to have to end up having to use every single element of the domain once. So indeed, in that case, it will be the case that every element of the domain appears once and only once in all of the rows corresponding to the non-zero elements. But if we're working with an infinite domain, such as the integers, then it doesn't need to be the case that each of these rows contains every element of the domain. It just has to be the case that no element of the domain appears more than once, and that's exactly proven here. I cannot have an element appearing more than once, otherwise you can prove that B and C are equal to one another, and therefore this picture's rubbish, basically. Okay, so all of these different entries in a row corresponding to an element that is not equal to 0 must be different elements of the domain, and as I say, if you do the equivalent thing here, that will refer to the columns, and again, columns for non-zero elements in the domain must contain elements of the domain only once. Not necessarily once and only once, just only once. It can't contain elements of the domain appearing more than once. Okay, so The only rows and columns then that actually don't obey this are the row and column that correspond to 0. They're the only row and columns where you have the same element appearing more than once. In fact, you have it appearing loads and loads of times, which is 0 in this case. All the other rows and columns in the multiplication table of an integral domain contain elements of the domain appearing only once. Again, if you're working with a finite integral domain, then it will have to appear once and only once. If you're working with an infinite domain, then obviously infinite set theory stretches and allows it not to have to obey that. Okay, but if you're working in a finite integral domain, the rows and columns not corresponding to the 0 element in the integral domain must contain every element of the domain once and only once. Okay, so we'll call it there for this video, and in the next video what we'll do is explore some theorems relating to integral domains in more detail.